Let's look at some additional properties that a linear transformation T from V to W has. T is said to be 1-to-1, 1-to-1, if it satisfies the following property. If T of U equals to T of V, then U equals to V. Okay, T is said to be onto if it satisfies the following property. For each W in W, there is a V in V such that T of V is equal to W. Okay, so T is onto if each W in big W is the image of some V. Okay, let's do an example. Let T from R2 to P2 be defined by this. Now, P is equal to this polynomial, V1 plus V2x. Show that T is 1-to-1, but not onto. Okay, so let's start with the 1-to-1 property. Suppose T of U equals to T of V. Okay, then U1 plus U2x, that's the polynomial that we get for U. That's equal to V1 plus V2x. And this is the polynomial that we get for V. Okay, but if these two polynomials are equal, then their corresponding coefficients are also equal. So U1 equals to V1 and U2 equals to V2. But then that means that these vectors, U1, U2, and V1, V2 are equal. Okay, so the vector U equals to V. But that's what we wanted to show. If T of U equals to T of V, then U equals to V. That's just what it means for T to be 1-to-1. Okay, now let's show that T is not onto. Let's pick some polynomial like this. Okay, well, then there is no V in R2 such that T of V equals to W. Okay, suppose there is. Okay, then t of v is this polynomial, and that's equal to w, which is this polynomial. Okay, but notice here we have an x squared term, but here we don't have an x squared term. This is a contradiction. Now let me explain this a little bit more. The set consisting of 1x and x squared, that forms a basis for P2, the set of all polynomials of degree less than or equal to 2. And every polynomial in P2 can be written uniquely as a linear combination of these basis vectors. So here we have 1x and x squared, and yet here on the other side we have v1 plus v2x. So that's a different way of writing this polynomial, but there's only a unique way of writing it, okay, as a linear combination of those basis vectors. Okay, so that's why we have a contradiction here. So our supposition that there was some vector v that gets sent to w, that's false. So t is not onto. Okay, let's do another example. Let t be this function from R2 to P0. Let it be defined by this. Where P is the polynomial that just gives v1. So P is a constant polynomial. Show that T is onto but not one-to-one. Okay, so let W be in P0. Then W is a constant polynomial. Let's just say A0 for some constant A0. Now let V be this vector. Okay, then V lies in R2, and T of V is equal to W, because T of V, that's equal to the polynomial P, where P of X is equal to the first coordinate here, A0. But that's just what W does, right? W is a polynomial which is equal to A0. And since these two polynomials are the same constant polynomial, they're equal. Okay, so T is onto. Now let's show that T is not one-to-one. Well, T is not one-to-one because T of this vector is the same as t of this vector, but 1, 0 is not equal to 1, 1. T of 1, 0, that's equal to the polynomial where p is equal to the first coordinate, 1. And t of 1, 1, that's the polynomial, let's say q, where q of x is equal to the first coordinate, which is 1. Okay, so p and q, they're the same constant polynomial, 1. So that's why they're equal here. Okay, but notice that the two vectors here are not equal, so t is not 1 to 1. Okay, let's do one more example. Let t from R2 to P1 be defined by this. Okay, show that t is 1 to 1 and onto. Okay, so let's start with the 1 to 1 property. Suppose t of u equals t of v. Well, t of u, that's the polynomial u1 plus u2x. T of v is the polynomial v1 plus v2x. And if those two polynomials are equal, then their coefficients are equal. Okay, so therefore these vectors are equal. In other words, u equals to v. Okay, so t is 1 to 1. Now let's show that t is onto. Let w be some polynomial in P1. So w of x equals some polynomial like this, where a0 and a1 are some constants. Now let v be the vector a0, a1 from here. Then v lies in R2, and t of v is equal to a0 plus a1x by definition of t. So we get this polynomial, but that's just w of x. Okay, so t of v is equal to w. Okay, we picked an arbitrary w in P1, and we found some vector v such that t of v is equal to w. So t is onto.